they ask, how do you balance this equation? I am not familiar with these fancy
It's okay.
science
Why don't you let me read it? And Nate, would you mind helping me out by drawing it on your screen? So you can just draw the chemical symbols, and I'm just going to read them to you as they're written. Okay. So you've got AS plus, and if you do me a favor, just leave a little space in front of each of the chemicals.
I'm leaving trying to do the underline like they did.
Excellent. So plus NaOH.
Okay.
Yields, so an arrow going to the right, yields Na3, and that's a subscript 3, a little 3 down below.
Okay.
AS, O, and then subscript 3 again, plus H2.
All right.
Okay, so if I was going to read this as chemicals, it's astenine or astenine plus sodium hydroxide yields, I am not actually sure what that chemical is, and hydrogen gas. But it's the chemical that I didn't know. It's some kind of a compound made of sodium, astenine, and oxygen. So what we're trying to do here is, this is actually something I'm teaching right now in my chemistry class, so this is kind of perfect. The idea here is based on what's called the law of conservation of mass. And the law of conservation of mass states that within a closed system, so if you're not losing anything to the outside world, if you run a chemical equation, whatever ingredients you put in, the mass of the ingredients put in should be equal to the mass of the ingredients that are output. And so from a simple perspective, what we want to do is make sure we have the same number of elements on the left as we do on the right. So the first thing that I'm noticing as I'm looking at this is, on the left side, I have sodium hydroxide, which has 1 sodium, 1 Na. But on the right side, I have 3 sodiums. So that means that my equation currently is not balanced. And what we're going to try to do is balance it to make sure we have the right number of chemicals of each type. Okay, so the first thing that we're going to do is, since I notice that there are 3 sodiums on the right, but only 1 on the left, is I'm going to put a 3 in front of the NaOH, the sodium hydroxide.
So right there.
Yes, indeed.
Right.
So that would mean that we're going to have 3 parts sodium hydroxide to end up yielding whatever we need. Now this is great because it means that if I'm looking, okay, so on the left, I notice that I've got 1 AS, 1 astenine, and on the right, I've got 1 AS, 1 astenine. So that's perfect and balanced. If I look on the left, I've now got 3 sodiums, and on the right, I've got 3 sodiums. So things are looking good. But when I multiplied that NaOH by 3, I also multiplied the O and the H in addition to the Na. So now I have 3 oxygens and 3 hydrogens on that left side. Now if I look at this compound, Na3AsO3, that's kind of perfect because it has 3 oxygens as well. So just by doing that one move, I've almost balanced this whole thing. I have 1 astenine on the left, 1 astenine on the right. 1 sodium on the left, or sorry, 3 sodiums on the left, 3 sodiums on the right. 3 oxygens on the left, 3 oxygens on the right. What's missing now is we've got 3 hydrogens on the left, but only 2 hydrogens on the right. And so what we want to do is get these balanced. And so what I would do is this. I would say, okay, what number could I multiply 2 by, since there's 2 hydrogens on the right, to get 3?
That would be 1.5.
That would be 1.5. So let's do that, if you don't mind. Let's write 1.5.
Oh, are you allowed to do that?
Oh, so technically no, and let me explain why. So, okay, normally when we're talking about these kinds of chemical formulas, we're talking about large quantities.
Right.
So the way I would read this now that Nate has it set up, and this is actually correctly balanced with one minor mistake. So the way I would read this is I would say, since there's no number in front of the AS, I would say 1 mole of astenine plus 3 moles of sodium hydroxide yields 1 mole of this chemical Na3AsO3 plus 1.5 moles of H2 gas. And that's doable because I can measure out 1.5 moles of hydrogen gas. But one of the problems is we often think about this as individual molecules. So an individual molecule, 1 molecule of astenine, combines with 1 molecule of sodium hydroxide to yield one molecule of these, and then we can't have 1.5 molecules of H2 gas. That's a problem. So what we do now, just to make them all whole numbers, is we're going to do whatever we have to that 1.5 to make it a whole number, and we'll do the same to all the rest. So what I'm really going to do is multiply all of these, and these numbers ahead of the chemicals are called coefficients. And so I'm going to multiply each of the coefficients by 2.
So guys, if you pay attention in math, you can also understand chemistry.
And I reference all the time, I say all the time to my students, you know, when we're thinking about these coefficients, think about your equations that you're doing in math. All sorts of different quadratic formulas, for example, are going to have variables with coefficients, right, often.
Right.
And so it's that understanding of if I know what a coefficient is in math, I can often be successful when that vocabulary comes at me in
Ooh,
science.
that reminds me to emphasize that then.
Please do. We
I
science
mean,
and
I
math
do
teachers should
emphasize
be
it, but I
coordinated
really need to emphasize that coefficients exist also
in other places.
other places.
Yeah.
A coefficient is not just a number
Not
in
just
front of
a
a
wonky
variable in
math
math.
term.
Yeah.
So anyways, to get back to the final answer,
Sorry.
we would end, no, that's perfect, thank you so much. So the final answer, we multiply each of the coefficients by 2, so we would end up with 2 AS plus 6 NaOH yields 2 Na3ASO3 plus 3 H2.
Now, if you're
So-
writing this out, like working the problem out, would you do it, and I'm just guessing here because I haven't seen this in a very long time, would you do it similarly like to you, how you do it in algebra?
So you don't
Kinda like
actually,
this,
so you
or-
would, yeah, my students actually were asking me literally about this today. They said,
Yeah.
shouldn't I put the chemical in parentheses if I'm going to multiply? And we don't do that since the chemical
Okay.
formulas don't have
So I'm gonna reset.
numbers. The only numbers in a chemical formula is the subscript. And in a
Right.
well-written chemical equation, it should be very easy to distinguish coefficients before
Okay.
with subscripts within. So we don't.
So
tend
would
to
I
do that.
just rewrite this as like 2
Yep.
AS plus 6, kind of just like that?
That's exactly the case.
I mean, the equality rule, this is just like an equation.
Okay,
I
so-
mean,
Right.
it's like,
So systems of equations are the normal way to solve this. With most chemical formulas, it's easy enough to just look at them and sort of go back and forth and figure out what do I need to add to one side to make it equal the other. But were you to have a more complex formula, and I should bring one in as an example, you can use systems of an equation.
I never did that in high school, but
solve
that is
this.
so cool.
So one of the issues we run into, right, as science teachers is we say, okay, is it worth taking a week to teach systems of equations?
No.
And it's usually not. So we teach shortcuts,
Well, they
hoping that
should
they're
know
going
it
to
in
get.
math.
They should, right? So they should be learning it in math, right? One of our great challenges, I think, is connecting all these different disciplines.
Subscribe!
Subscribe!
Come on, push the button.
You know you want to.
Do it.